All right, so we are going to start today with the law of sines. The second section is pretty short. It's only 11 slides, so we might end up finishing today. If we do, awesome. You would probably end up having Wednesday off to work on things, but let's take it one day at a time and we'll figure it out. Because I definitely want you guys to have enough time to work on things, but I also don't want us to run out of time. And I'm pretty sure I have us going all the way up to and including finals week, because we have chapter 10 and 11 after this as well. So, all right, let's go ahead and get started. So law of sine is going to be very similar to law of cosine is going to be very similar to the law of sines. You can see your three objectives there. We're going to solve triangles using side angle sides, solve using side, 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 and solve applied problems. The reason why we are focusing on side angle side and side is because those are the two cases that deal with law of cosines and not law of sines. What's kind of nice for you guys, as opposed to whenever I was being taught trig, yes, we were taught law of sines and cosines, but we weren't really taught them as nice as you guys are being taught them. So we knew the different cases, but then we were kind of just left to our own devices to figure out when you can use law of sines versus when you can use law of cosines. So it's kind of nice that this textbook is kind of giving you those problems on a silver platter a little bit. So that's kind of nice. So if you haven't already worked ahead in things and you need to write down the law of cosines, go ahead and write this down. If you are writing your own trig cheat sheet, this is definitely something that you want to have on the sheet. You want to write this down. You will use this for your homework, you will use it for your quiz, and you will obviously use it for the chapter 9 exam. Chapter 8 exam, public service announcement, is technically due tomorrow night. If you need to, because of work reasons, XYZ, whatever, no pun intended, you may turn it in to me as late as Friday. But I would like to get you your results back by Monday at the latest. So try not to go too far past Friday. If you need me to open anything up for you in Pearson, please let me know and I will do so. We need before we switch over to the whiteboard to do some problems. So it says the law of cosines is the square of one side of a triangle equals the sum of the squares of the other two sides minus twice their product times the cosine of their included angle. So if you couldn't figure that out based on the mathematical definitions, there is your word definition for you. For those of you who like words more than math, which does not include myself, but hey, more power to you. All right, so the next question should be, yep, there it is. You can write it out. We're going to head over to the whiteboard to figure it out without you being just given the solution. Okay. All right, so the question is, if you are given A equals 4, B equals 5, and angle C equals 50 degrees, we're going to be able to use the law of cosines. So the first thing we're going to find is little c. Okay. So we're going to pick the law of cosines that has us solving for c. All right. And it's going to be a squared plus b squared minus 2ab times the cosine of big C. And then to find just C, you'll take the square root of all that. So 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of 50 degrees. I'm not going to insult your intelligence by figuring all that out for you. So I will just write down that you will get approximately 3.91. And I don't know about you guys, but I always write down units if they don't give it to me. So that's how I do that. Now, Pearson will always ask you to find all of the missing pieces. So that is what we're going to do with this problem as well. So now that we found little c, we can use little c to help us find big A. Okay, so we're going to start out with the law of cosines that deals with big A. So we start out with a squared equals b squared plus c squared minus bc cosine big A. All right. Now A is what we're looking for, so that means we actually have to go through and do a little bit of algebra manipulation. So if we go through and do that, we end up with the cosine inverse of b squared plus c squared minus a squared all over 2bc. Now, it's completely up to you guys. Most of the trig cheat sheets do not have this different representation. They just make you do it every single time. But if I were you guys, I would just go through and figure them all out, so then you could have big A, big C, and big B. But that's completely up to you. You can change it every time. If you go through and plug everything in, you are ending up with a degree of 51.6 degrees. Now, here's what I will tell you is interesting. I feel like trig is when we deal with this section of trig, I feel like it's the only trig where they go through and they basically tell you, feel free to use the unknowns that you're finding in order to find other unknowns. It's really something that I have to kind of think about, but I mean, it is what it is. Now, to find big B, we can do two different approaches here. We do have 2 out of our 3 angles, so we could subtract them from 180. However, because this is the law of cosines section and you are learning the law of cosines for the first time, they do have us go through and use the law of cosines. You can choose not to. It really ends up working in your favor either way. I think most of the homework, you can get away with it being just subtracting from 180. You just kind of have to be careful on when you do the subtracting from 180 versus not. Okay, when you plug everything in, you end up getting 78.4 degrees. And you can check all of that. All right. Any questions with that example? Like I said, these last 3 sections are pretty short. So, and I will have everything recorded and up for you, hopefully by the end of today. So if I go a little bit too fast, make sure that you watch the video. All right, so we're going to look at example 2 now. And example 2 deals with objective 2, which is side, side, side. So we are going to be given all of our sides this time. So A equals 5, B equals 4, and C equals 7. Okay, so if you wanted to draw out your triangle, you could. Obviously, we are going to start with finding some angles. So I chose to find them in order, I'm pretty sure. So I found A first. You guys can choose to go in any order you want. So A equals the cosine inverse of A squared, or B squared, which is 4, so 4 squared, plus C squared, minus A squared, all over 2 times A times C. And if you work that out, you end up getting 44.4 degrees. Okay. All right, finding B, very similar. Cosine inverse. We're gonna end up with 5 squared, which is A squared, plus C squared, minus B squared, over 2 times A times C. You plug that in and figure it out, and you end up with 34 degrees. Okay. Now this one does have us using the original technique of subtracting from 180. Like I said, kind of just depends on the example that you're doing or the problem. So we're going to take 180 minus 44.4 minus 34. And we're going to end up with big C equaling 101.6 degrees. Okay. Obviously, you can prove to yourself if that is correct by simply taking the 3 angles, adding them together, and dividing, and seeing if you end up getting 180. Okay. Make sure you guys are asking questions if you have any. Like I said, with it being such an easy, quick section, I doubt you'll have any, but you never know. So the next objective we're going to do is the applied problems. So this is example 3, and I am going to switch back over into the slides for you. Okay, can you see the slides again? I just want to make sure that they're showing up. Okay, you can go through those if you want. They are up on Canvas, and I guess if you pause them quickly enough, you could catch them. So this is example 3. We are going to be working with correcting a navigational error. You can go ahead and take away whatever pullouts you want to pull from this problem. A motorized sailboat leaves Naples, Florida, bound for Key West 150 miles away. Maintaining a constant speed of 15 miles per hour, but encountering heavy crosswinds and strong currents, the crew finds after 4 hours that the sailboat is off course by 20 degrees. So they want us to figure out how far is the sailboat from Key West at this time, through what angle should the sailboat turn to correct its course, and how much time has been added to the trip because of this. And then it says assume that the speed remains at 15 miles per hour. All right, so the first thing I wanted to show you guys was this nice little drawing. So I went ahead and drew my own. I would highly suggest you do the same thing. And then what that does is it kind of gives us a little bit of a direction of what to look for. And then once you guys have this drawing, I'll go ahead and switch back over to the whiteboard. So the first thing we want to find is this little X here. And what do you notice is you kind of have to figure out based on the drawing what we're going to end up using to find X.
Use the law of cosine.
What's that?
So we could use the law of cosine to find x.
Yes. Yes, we're going to use the law of cosines to find X. And I will go back over into the whiteboard and we will start that process. Okay, so the first thing we're going to do is we're going to do x squared equals, and we're going to use 150 squared plus 60 squared minus 2 times 150 times 60 times the cosine of 20 degrees. Okay. And once we find all that, we'll take the square root. This ends up working to 9185.53 under the radical, which leaves you with x is approximately 95.8 miles. When you write it out, the sailboat, not board, the sailboat is about 96 miles from Key West. Okay. So the next thing they want us to figure out is through what angle should the sailboat turn to its original course. So now that we know all three sides of the triangle, we can use law of cosines again to find angle A, which is opposite the side of the 150 degrees. Okay. So now we're going to find angle A. Okay. We end up taking, if you work everything out, you end up getting the inverse, cosine inverse of negative 0.8406, which works out to 147.2 degrees. But that is actually not your answer. What do you think you have to do to figure out what theta is? What do you guys think you have to do? What do you think a good guess is? So let's think about it. We had our original 20 degrees up top. What we just found was the angle across from the 150, and they're down here at X. So is that the angle they have to guide the boat towards? Like, is that where we want to shoot through? Or do we have to do maybe something? What do you think we have to do?
We subtract 90 to 147.
Close. So we're gonna take, it may end up being the same. No, I don't know if it would be the same answer, but we're gonna take 180 and subtract the 147.2. Okay, so that's gonna help us find our theta. You can try it the other way. You can try taking the 147.2 minus 90 and see if you end up getting the same answer. You might. Okay, so then you're going to end up with a theta of 32.8 degrees. And that is the angle that's going to write your course. As far as how we answered the last part, which says how much time has been added to the trip because of the strong winds and such, you have to take the total length of the trip is now 60 plus 95 miles, which 96 miles. So our total mileage, our total miles. Hello. Hello. So our total miles is, they're going to be 60. So the publishers use 95, so we'll just use 95. It's fine. So we'll end up with 156 miles. But now we need to take that 156 and we have to add on an additional 6 miles. So then 6 miles would work out to how many hours? are parts of an hour? You guys know? I'll pull it back over into the slide. Okay. So we're looking at this part. The total length of the trip is now 60 plus 96. Oh, I couldn't read my writing apparently. So that gives us a total of 156. The extra 6 miles will only require about 0.4 of an hour or 24 minutes if we keep a constant speed. Okay. Any questions on 9.3? Any questions on the law of cosines? Okay. So if I were you guys, I would try to get caught up to where we're at homework-wise with Pearson. But again, I understand if you want to focus on your exam. The other thing I will briefly. All right. So let's look at area of a triangle. So we're going to find the areas of side angle side triangles and the area of side 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 triangles. So go ahead and write down your first theorem. And honestly, this section is super, super short. And if you guys need to, if I go too fast, please watch the video. I'm going to make sure I put it up today and you guys can just, you can pause it as you need to pause it. Here are your formulas. So K equals 1/2 AB sine C, K equals 1/2 BC sine A, and K equals 1/2 AC sine B. You can kind of see why it would be shoved into this chapter. Slightly looks like a variation of the law of sines, a little bit. All right. Again, like I said, I'm recording everything so we can go a little bit quicker and you can go back and catch up. All right, so theorem 2, the area K of a triangle equals 1/2 the product of two of its sides times the sine of their included angle. Again, that's just giving it to you in Englishy terms. So let's go over to the whiteboard. Okay, so this is the problem we're going to focus on. If we are given the following, find the area K of the triangle for which A equals 5, B equals 3, and angle C equals 50 degrees. Okay, so that's our problem. All right, so first off, let's consider our solution formula. So we have A, B, and the angle is C. So what formula do you think is going to help us out?
1/2 a times b times the sine of c.
There you go. So obviously we want to use the one that employs all the things that we have. And then we'll just plug them in. So 1/2 times 5 times 3 sine of 50 degrees. So K ends up being approximately 5.7 units squared. Or square units, however you want to say it. Okay. Now, the following theorem, okay, here's your theorem thing. Orion's formula. The area K of a triangle with sides A, B, and C. So we're going to solve for the following. And then notice where they say that S is equal to 1/2 your summation of A plus B plus C. Okay. So make sure you write that down. And once you're done with that, we'll go over and do the last example. Okay, so let's go into the whiteboard. All right, so if we are given, find the area of a triangle whose sides are 5, 6, and 9. We're going to use our formula. So first thing we have to find is S. S equals 1/2 the summation of A plus B plus C. Okay, so if we figure that out, we're going to end up getting, let's see, 5 and 6 is 11, plus 9 is 20, 20 divided by 2, so we get S equals 10. All right. And now we have to plug it into the formula. So K equals the square root, and then we're just going to plug everything in. So S is 10, and then it was S minus A. So 10 minus 5 will give us a 5. 10 minus 6 gives us a 4. And 10 minus 9 will give us a 1. So K is approximately equal to, if we solve it up here, we'll get the square root of 200. So that's going to be 10 square root of 2 square units. Any questions at all regarding how we find the area of a triangle in these cases? Okay. We have 40 minutes, so we're going to try really hard to get through the last section. All right, so we're looking at section 9.5, simple harmonic motion, damped motion, and combining waves. Okay, so we're going to try to build a model for an object in simple harmonic motion. We're going to analyze simple harmonic motion, analyze an object in damped motion, and graph the sum of two functions. So I think you guys can kind of see with this section that we're definitely starting to overlap a little bit with physics. So that is why, trig and physics tend to go hand in hand a little bit more so, I feel, than with the calc sometimes. But obviously we know that calc is also involved in physics. All right, so let's look at this example, or I guess rather statement. In the figure, the point B is the equilibrium or rest position of the vibrating object. The amplitude is the distance from the object's rest position to its greatest displacement, either point A or point C in the figure. The period is the time required to complete one vibration. That is the time it takes from going from A to B to C back to A. Okay? And I'm not sure if it's going to tell you, but clearly you can see here that when it's in the A positioning, the spring is being compressed. And then when it's in the C positioning, the spring is being stretched. Okay. I am not going to require you guys to know the vocab, but I can tell you that sometimes Pearson has you required to know the vocab. So you may end up seeing this in your homework. All right. Simple harmonic motion is a special kind of vibrational motion in which the acceleration A of the object is directly proportional to the negative of its displacement from its rest position. Okay, you can see the little here you go. Probably want to pay attention to that. The graph shown in the figure describes the displacement of an object from rest as a function of time t, assuming that no frictional force is present. Why are we happy that we're not looking at frictional force? Which I can tell you that sometimes in physics you're going to have to consider it.
Because friction sometimes messes up with your calculations.
Right, so you're not going to have something as nice as this curve here, okay? So we have to pay attention to that. All right. Theorem 1. Go ahead and write it down. Okay, so recall from when we were talking about sinusoidal curves and figuring out those equations. Again, our amplitude is positive, so you have to remember to take the absolute value of A, okay? And then, obviously take a look at that. We're once again considering our sinusoidal curves. So it completely makes sense as to why this is in the section that it's in. Right? And like I said, if we're going a little too fast, make sure you watch the video. You can pause. You can also check out just the slides on Canvas. All right. Frequency. What does frequency remind you of?
How repeated has appeared or something?
Yeah, so I think it kind of reminded me of how we found omega before, but obviously we're using omega to find frequency. So so go ahead and write that down. I'm not going to read it to you. We are going to end up using frequency in the next. Actually, we don't. Okay. So we are going to move over into the whiteboard, but before we do, I want you guys to go ahead and write everything down on this slide. So example 1, we're going to build a model for an object in harmonic motion. So there's our figure to the right. Make sure you draw it out, or at least pull away from it what you think you need to pull away from it. So it says, suppose an object attached to a coiled spring is pulled down a distance of 5 inches from its resting position and then released. If the time for one oscillation is 3 seconds, develop a model that relates the displacement of d of the object from its rest position after t seconds in time, assuming no friction. So let's go over into the whiteboard. Okay. So when the object is released, we know that's going to happen at t equals 0, right? Okay. The displacement of the object from the rest position is -5 units. So d is equal to -5 units. Okay. Okay, so because of these two items, we're going to work with cosine. So d is equal to the cosine. Whoop, I forgot to include a. A cosine omega times t. All right. Now to figure out the amplitude, what do we know about, what do you think we can use right now that'll help us with our amplitude? It's basically the only thing that makes sense at this point, okay? Our amplitude is going to be the absolute value. So it's going to be the absolute value of -5. Right? But now we have to figure out our period. So what are we going to do there? So 2 pi over omega. What do we know about the period? What did it tell you about the oscillation? Okay. So that means we have 2 pi over 3. Why did I go with 3? Think back to the problem. What's the problem tell you in it that makes sense? I actually think they're answers wrong on the slide. So make sure I show you guys that. Do you guys agree or disagree? All right. For the sake of the recording, the 3 comes from the oscillations in the problem. I'm going to go ahead and clear it. We're going to go back. All right, so here's why I think their answer is wrong. We just did all of this over in the whiteboard. Then they find the amplitude is 5, and the period we know is 3 because of the oscillations, 3 seconds. But then look what their answer said it was -5. Now, why would we be told to use the absolute value of -5 as 5? And then they want to put it back in as a -5. I would go with the absolute value. I think this is wrong. I don't think there should be a negative here. Why is this not letting me? Well, it won't let me write on it for some reason. I don't know why, but I would not use that as the negative there. Okay, so this is the next example we're going to look at. Okay, so suppose that the displacement d in meters of an object at time t in seconds satisfies the following equation. D equals 6 sine of 2t. Describe the motion of the object. What is the maximum displacement from its rest position? And what is the time required for one oscillation, as well as what is the frequency? So before we go looking at the solutions, what can you guys tell me? What can you tell me about the equation itself? What can you pull out of it?
So the equation is using sine instead of cosine.
Yeah, so it is sine instead of cosine, but what can you tell me about, like, what can you pull out of this? So let's go over to the whiteboard. So the problem is 6 sine 2t. Okay, d equals. Now our generic is d equals a sine omega t. So what can we pull out?
The amplitude.
Yep, so the amplitude is 6. We also know that the omega is 2. And then in terms of just answering A, would you consider that a simple harmonic motion? You would, right? Because that follows the exact same pattern, doesn't it? So because that follows the same pattern, then you say that it's a simple harmonic motion. Now for B, B wanted to know the maximum displacement of the object from its resting position. So what's that going to be?
Wouldn't it be 6?
Mm-hmm. Okay, you just find that by taking the absolute value of A. All right. Which I guess that's why they had the negative in before for their answer, because it was pulled downward. So I guess that's why they left it as a negative. All right, so the time required for one oscillation is the period. So here's what we know with that formula. We know that 2 pi over omega will be the frequency. So then 2 pi over what? We just found omega, it's 2. So then we get pi seconds. So pi. The last one is D. I guess that is not the frequency part there. Oh no. That was annoying. Okay. So that is the time, this is the time for just one oscillation. So this is for one oscillation. Okay. So to find D, frequency is the reciprocal of the period. So frequency is equal to omega divided by 2 pi. So that's going to be 2 over 2 pi, which is just 1 over pi. Oscillations per second is our units. Okay. Okay. All right. Any questions on this one? I highly suggest that you ask questions now versus later. All right. All right, here you go. Theorem 2, damped motion. The displacement d of an oscillating object from its at-rest position at time t is given by the following, where b is the dampening factor or dampening coefficient, and m is the mass of the oscillating object. Here, the absolute value of a is the displacement at time t equals 0 and at 2 pi divided by omega. is the period under the simple harmonic motion, therefore no dampening. Okay. Again, if I'm going too fast, you can always watch the video or check out the slides yourselves. All right. For example 3, we're analyzing a damped vibration curve. You want to analyze the damped vibration curve. They give it to you. We're just going to focus on the PowerPoint because I just don't think I would be neat enough to do it in the whiteboard. So the displacement D is the product of y equals e to the t over pi and y equals cosine of t. Using the properties of absolute value and the fact that the absolute value of cosine of t is greater than or equal to 1, sorry, less than or equal to 1, we have the following. And then they went through and they kind of made it a little bit nicer. Why is it saying that my share screen is stopped? Sorry, guys. Must have shared the wrong PowerPoint. Okay, any questions on this? Okay. All right, this means that the graph of D will lie between the graphs of y equals e to the negative t over pi and y equals negative e to the negative t over pi. We call this bounding curves of D. Also, the graph of D will touch these graphs when the absolute value of the cosine of t is equal to 1. So that's going to be at t equals 0, pi, and 2 pi. And they also break down the x-intercepts. Okay. I would highly assume that you'll have to do something similar to this on Pearson. And I really hope we're not going to have to draw it. All right. Okay, the sum of two functions. We use a method of adding y coordinates to the graph. So the first graph, the component functions are y equals f sub 1 of x equals x over 2. You can see that from what you were given. Right here. There's y sub 1, or I guess f sub 1. All right, and then the second part, f sub 2. You could consider them y sub 1 and y sub 2. All right, you can see your coordinate plane. Right. Really, all of this should be pretty much a review for you based on the, I think it was chapter 7. So it's just kind of all coming back, and now we're just plotting them together. If you have a hard time with it, just email me. I'm sure we can work through the problems together in a Zoom session. But I really feel like that's just stuff that you guys can work on independently. And just for the sake of the recording, I'm going through one more time and just make it so you guys can pause it if you need to pause it. Okay.